Imagine a quiet room, late at night. The lights are low. There is the soft hum of electronics somewhere nearby, and the gentle thrum of air flowing through a vent. A screen shows a field of stars, so many that your eyes don't know where to rest. In this quiet, you listen, not with your ears, but with light. The universe is speaking in color, in tiny dips in brightness, in faint whispers of infrared heat. Somewhere, beyond the familiar glow of our own sun, a planet turns. It is midnight there, and midday, and 1,000 sunsets, all at once. It could be breathing. This is the scene we come back to, again and again, when we talk about biosignatures, those subtle fingerprints of life left on the canvas of a planet. The word biosignature sounds technical, but the idea is simple. It is any clue that says, softly, someone living was here. On Earth, that could be oxygen in our air, or the gentle way plants reflect red light, or the seasonal rise and fall of gases as the planet grows and rests. On worlds far away, we cannot touch soil or scoop water or listen for birds, at least not yet. So instead, we listen for patterns. We watch how a planet filters starlight when it crosses in front of its star. We measure the glow it gives off as it warms, cools, and spins. We look for chemistry out of balance breath that should not be there without living mouths, living leaves, living microbes. NASA's search for alien biosignatures is not a chase scene. It's not a sudden reveal. It is patient, careful, and slow by design. It moves at the pace of light, the way a tide moves a pull, a return, another pull. Scientists ask, what would life do to a planet? How would it bend light, push chemistry into unexpected corners, draw down some gases, and release others? The answer is a story told in millions of data points, stitched together under a sky so wide it almost feels like a dream. Take oxygen, for instance, the airy confidence of it. On Earth, oxygen is the echo of photosynthesis, the exhale of plants and algae, and tiny organisms that turn sunlight and water into sugar and fuel. Without life, oxygen is quick to disappear, to bind with rocks, to rust iron, to slip away. If we were to find a planet rich in oxygen and ozone, it would make our hearts lift. Yet soft pause, we have to be cautious. The universe is clever. Under certain circumstances, a planet can make oxygen without life at all. Ultraviolet light can split water. Hydrogen can drift to space. Oxygen can pile up. A planet can mimic the breath of forests without a single leaf. So a biosignature is never just one clue. It is a chorus. Maybe oxygen appears alongside methane, a gas that should burn away in oxygen's presence unless something keeps making it. Maybe there is water vapor, carbon dioxide, and a steady, seasonal rhythm in their levels, like the rise and fall of Earth's carbon cycle breathing with the seasons. Maybe the surface glints at a certain angle, the way sunlight flashes on an ocean, or polarizes light in a way that suggests pigment leaf-like pigments that grab and reflect specific colors. Behind the scenes, NASA's approach is a web of observation and humility. Space telescopes sniff light across wavelengths. Instruments on rovers and orbiters taste the chemistry of soils and ice. Lab teams on Earth cook up alien world atmospheres in glass chambers and bombard them with starlight, checking for false positives, rehearsing the tricks nature might play. Biologists study life at the edges, in boiling springs, in salt lakes, in Antarctic brine, and ask what signatures these tough survivors leave behind. There is a shared intention running through all of it. Make a map of what life can do, and then listen for it in the faintest places. In the stillness of our late-night room, with the humming electronics and the gentle glow, you can feel the scale of the question. How do you detect a living world by looking at it from light years away? How do you separate a real breath from a gust of chemistry that only pretends to be alive? In the careful, quiet style of NASA's science, the answer begins with history, with a few daring experiments, and with a planet we know better than any other. Earth. Just before sleep, hold that thought. The Earth, seen from far away, once had to prove itself to our own machines. What did it whisper back? And how did that whisper set the tone for the search far beyond home? Years ago, a spacecraft named Galileo swung past Earth on its way to Jupiter. It carried cameras and instruments tuned to light our eyes cannot see. Carl Sagan and colleagues posed a playful, profound challenge. Pretend we don't know this blue world is alive. Can a machine, glancing from space, tell the difference? Can it find the breath and the pulse in the spectra? Galileo listened. It measured our atmosphere and found oxygen abundant and reactive. It found methane, that flammable, fragile gas that should vanish in oxygen's company unless something keeps replenishing it. It noticed a radio hum narrow band, structured, not easily made by nature. And it caught the red edge of vegetation, the way chlorophyll reflects a sudden step of red light just beyond what our eyes see. It is as if the planet flashed a subtle badge, green by day, ruby at the edge. Taken together, these were not just clues, but a near confession. Sagan wrote of this in wonder. With one flyby, we learned how life might look from afar. But the lesson that followed was just as important. 40 years ago, 2 NASA landers called Viking touched down on Mars. Their instruments sniffed the soil for breath and crumbs of metabolism. One experiment, the labeled release test, saw gas release after adding a nutrient, as if microbes were eating and exhaling. Another experiment, a gas chromatograph mass spectrometer, did not find organic molecules. It was a puzzle. Was Mars alive, or was Mars a keen alchemist, doing chemistry that fooled our tests? Decades later, we found perchlorates, oxidizing salts in the Martian soil that would have destroyed organics when heated, explaining why they were not seen. The earlier signal became ambiguous. The story slowed, became more careful, and more precise. From these early adventures, NASA and the astrobiology community learned 2 quiet rules. 1. Don't trust a single test. Life is complex, and so is geology. 2. Context is everything. If you see a gas, ask what the world around it is doing. How bright is its star? How lively its volcanoes? How dry its deserts? How salty its water? A biosignature is not a single exhale. It is a relationship between a planet and its star and its history. Out of this, frameworks emerged. Scientists began sketching ladders and scales to describe how confident we should be about possible life. Think of a ladder of life detection. At the bottom rung, there is a hint, a suggestive pattern in a spectrum, a curious bump in a curve. On a higher rung, there is a second line of evidence, independent and consistent. Then more, multiple instruments, careful calibration, reproducibility. At the top, there is a tapestry that hangs together, with no good non-biological explanation left. NASA researchers have proposed confidence scales to report these steps publicly, to keep us honest in the glow of hope. A whisper is a whisper. A chorus is a chorus. We should name which we have. In parallel, at benches and in clean rooms, the craft of detection grew gentler and more exact. Contamination control became a solemn ritual. Instruments were sterilized with care. Teams rehearsed handling tiny samples without breathing the ghost of Earth into them. Lab scientists prepared blank samples and ran them through instruments to see what a machine's own breath might look like, because machines exhale too, in little data quirks. Computer models of planetary atmospheres grew from childlike sketches to rich, layered paintings. They could include star flares, magnetic fields, oceans, clouds, haze, even the way light bounces inside a planet's sky. And above us, the telescopes multiplied. Kepler watched a patch of stars and counted their small dimmings, finding planets by the thousands. TESS, its successor, looks across the whole sky. Bright stars nearby, familiar neighbors. Around these stars, a family of small, rocky worlds emerged, some the size of Earth, some a little larger, some nestled in that gentle region where liquid water could persist on a surface, the so-called habitable zone. They are not promises. They are invitations. To see whether any of them breathe, we needed to learn the language of light more fluently. Spectroscopy, the splitting of light into colors, became the dictionary. Each gas in an atmosphere has favorite colors it absorbs or emits, like threads in a woven pattern. Water vapor, carbon dioxide, methane, oxygen, ozone, nitrous oxide, each leaves a distinct stitch. If a planet passes in front of its star, a thin sliver of starlight filters through the atmosphere. Gases in that halo eat certain colors. The starlight that comes through carries the recipe of the air. If a planet slips behind its star, the loss of its own thermal glow tells another tale. If we can blot out the star's glare and see the planet directly, we can weigh its light across wavelengths, like measuring the rich scent of a distant kitchen. And yet, scientists know softly that everything about this is hard. Stars have spots and flares. Photons are few and fickle. The signal of a small planet is like a moth skimming the face of a floodlight. We are listening to whispers in a crowded, windy room. So the next part of the story is about craft. How we learn to hush the room. How we build instruments that stare, hold their breath, and measure without trembling. Let's follow the path of that light. Let's watch it hit a mirror, pass through a slit, scatter into color like rain in a prism, and touch a sensor that can count single photons. There, in this gentle rain of particles, is the chemistry of a world you will never stand on. What does NASA do with that rain? How does it turn a faint rainbow into a possible sign of life?
A telescope is a bowl for catching light. Some bowls are small and quick and swiveling. Some are enormous, cool and steady, like lakes on mountains. Some are above the air, their mirrors folded like origami in a fairing, then opened far from home with the patience and care of a ritual. The Hubble Space Telescope made the first careful detections of starlight filtered through alien skies. It tasted sodium in the atmosphere of a hot giant. Later, Spitzer, with eyes in the infrared, measured the heat of worlds too close to their stars, mapping day and night. These were not living worlds, but they were a school for our senses. With Kepler, we learned that rocky planets are common. With TESS, we found nearby targets we could, in time, study in detail. And with the James Webb Space Telescope, a new hush fell over the room. Webb can spread light and count colors with exquisite sensitivity, especially in the infrared where molecules sing their strongest notes. On some exoplanets, Webb has already seen carbon dioxide, water vapor, hints of methane. It has captured the complex brew of gases around hot exoplanets the size of Saturn or Neptune. For smaller, worlds-truly Earth-sized planets, the signal shrinks. But the method holds. Around small, cool stars, where an Earth-sized planet blocks more of the starlight and the atmosphere is a thicker halo relative to the star, the whispers become more audible. Systems like TRAPPIST-1, a family of 7 Earth-sized planets, become natural amphitheaters. We listen there with care. We check our assumptions. We wait. What do we hope to hear? Not just one gas, but a chord. Oxygen and ozone are compelling, but we analyze the star as well. Around certain stars, especially young red M dwarfs that are prone to flares, oxygen can accumulate abiotically. If we see oxygen without the subtlest trace of water or in the presence of carbon monoxide, alarm bells ring. Perhaps the oxygen is not a breath, but a photochemical artifact. Methane offers its own songs. It can be generated by volcanism or water rock reactions. But a lot of methane alongside a lot of oxygen would be strange without life. Nitrous oxide is rarer, but is biologically produced on Earth. Its presence would be intriguing. A planet rich in CO2, H2O, a whiff of CH4, and a trace of O3, balanced in a way that suggests thermodynamic disequilibrium, begins to tell a richer story. Disequilibrium is a simple idea. Left alone, chemicals settle down. They drift into balance. Life refuses to settle. It keeps stirring the pot. Beyond gases, we look for surfaces. The vegetation red edge, that plant-like reflectivity jump near 0.7 microns, is one such surface clue. With future telescopes that can directly image Earth-sized worlds, we could map how a planet reflects color as it spins. Bright land, dark ocean, cloud swirls, 3-day light curves can sketch continents. When the star's light hits at just the right angle, a smooth ocean can throw a spark of specular glint. That flash and its polarization signature would be the wink of water, a sea silently catching the sun. Polarized light can also whisper about aerosols, clouds, and pigments. Some biological pigments scatter light with a tiny twister chiral polarization linked to the handedness of life's molecules. These are delicate signals, tender to noise and distance, but they are part of the toolkit we are refining now. Inside computers, the work is part physics, part poetry. We build retrievals, models that can take a spectrum and explore millions of possible atmospheres that might produce it. We ask, given this rainbow, what combinations of gases, temperatures, and clouds fit? The answer is never unique. Many atmospheres can mimic each other, so we bring context. What is the mass and radius of the planet? How much light does its star deliver? In what colors? How active is the star? Could haze obscure features? Are there volcanic markers like sulfur dioxide? Is there carbon monoxide, which hints that oxygen might be false? We let the numbers narrow the universe of possibilities. Planetary scientists bring Earth as a teacher. They simulate our planet as it was long ago. Before the Great Oxidation Event, Earth breathed mostly methane and nitrogen, with carbon dioxide and a haze that turned the sky into a softly filtered lens. In those epochs, there would have been no oxygen signature, and yet life thrived in microbial seas. So a living planet might wear a Titan-like veil. It might be subtle. A cloud deck could hide the strongest gas features. A world with oceans could breathe seasonally, shifting CO2 and O2 as forests grow and rest, but clouds might smear the signal into a gentle hum rather than a spike. We learn that no oxygen is not no life. We learn that patience and multi-wavelength observations are the rhythm of honesty. This is why NASA's plans stretch across years and decades. The Nancy Grace Roman Space Telescope will fly a coronagraph technology demonstration, a way to cancel starlight from within the telescope so a planet can be seen beside its sun candle next to a lighthouse. The idea of a star-shaded external flower petal screen that flies tens of thousands of kilometers from a telescope to block a star's glare has been studied as a path to reveal Earth-like planets near Sun-like stars. And a future mission concept, the Habitable Worlds Observatory, recommended by the astronomical community, is being shaped with one quiet intention: to detect and characterize Earth-sized planets around nearby stars, and to search their light for the chords of life, while eyes look outward. Other instruments listen at home to the Earth itself as an exoplanet training ground. A mission once called Epoxy turned a deep space camera back toward Earth to watch our own planet flicker like a distant dot. Extracting continents and clouds from brightness changes alone. The DSCOVR spacecraft, sitting between Earth and Sun, watches our full disk day by day, letting scientists test algorithms for mapping pigments and aerosols from the faintest hints. In this way, our home becomes a laboratory for knowing others. We have learned to be careful. We remember the phosphine debate in Venus's atmosphere, tantalizing hint, then a slower, more nuanced conversation about instruments, calibration, and the complexity of planetary clouds. We remember the excitement around possible methane on Mars and the complexities of measuring a ghostly gas that fades and flows with the wind. Every time we think we hear a breath, we lean closer, hold our own breath, and check the room again. In the next chapter, the search turns inward in another way. NASA's quest for biosignatures is not only about light years and distant suns. It is also about touching rocks and ice in our own neighborhood, where oceans hide under shells of ice, where rivers of methane run below a hazy sky, where dusty plains keep secrets fossilized in grains. Here too, we listen for life not as a chord in a rainbow, but as a pattern in a pebble.
Closer to home, the search for biosignatures becomes tactile. You could almost hear the crunch of a rover's wheel on a Martian pebble, the soft tick of dust on a deck, the whisper of wind over an aluminum mast. The sky is butterscotch. The horizon is patient. On Mars, NASA's Curiosity rover carries a miniature chemistry lab called SAM, which breathes in Martian air and tastes powdered rock. It has found organic molecules in ancient lake sediments, rings of carbon and hydrogen preserved in mudstones. It has tracked tiny puffs of methane that wax and wane with the seasons, a puzzle still unresolved. Methane on Mars could be geologic, from water-rock interactions deep below. It could be biological, from microbes eking out a living somewhere dark. The planet itself is both suspect and witness. Perseverance, Curiosity's younger cousin, explores a fossilized river delta, a place where fine sediments once settled in calm water, good at trapping fragile organic clues. It drills, caches samples in tidy tubes, and places them gently on the ground. A future campaign aims to bring these samples to Earth's best laboratories, where every whisper can be measured with extreme care. We design clean rooms, carefully choreographing how air will flow, where gloved hands will move, how to keep Earth's own life from singing into Martian rocks. In the icy darkness beyond Mars, Europa, one of Jupiter's moons, drifts with a cracked white shell and a global ocean beneath. There is heat inside, stirred by tidal flexing and chemicals. This ocean meets rock at the bottom, where vents could pour warmth and energy into water. NASA's Europa Clipper will fly by again and again, sensing the thickness of the ice, tasting traces of vapor if they appear, analyzing salty grains lofted above the surface. It is not a life detection mission. It is a habitability mission. It will ask gently, is this a kitchen where life could cook? Are the ingredients there? Is the heat right? Are there ways to cycle nutrients? Knowing this makes the next step firmer and safer. Farther still lies Enceladus, small and brilliant, trailing a ring of ice. Cassini flew through its plumes and found water, silica grains likely born in hydrothermal vents, and hydrogen chemical energy that microbes on Earth would love. It found organic compounds, the building blocks of complex chemistry. Enceladus tells us that oceans with energy exist in the cold. It invites us to come back with instruments tuned to life's sense, certain amino acids, certain lipid patterns, certain isotopic preferences. And then there is Titan, moon of methane rain, rivers carving through dunes, lakes of liquid hydrocarbons under an amber haze. The Dragonfly mission will fly there on rotors, a hummingbird in a sky thicker than ours, touching down, sniffing, launching again. Titan's chemistry is rich, exotic, prebiotic. It may not host life as we know it on its surface, but it may preserve steps toward life, recipes in the sand. If life on Titan exists somewhere, for instance, in a water ammonia pocket below the ice, it would be unlike anything we've met. Our biosignature toolkit stretches to accommodate not just Earth-like life, but life-like life, patterns of complexity that persist, harvest energy, and leave organized trails in chaos. How does one recognize such patterns? In the lab, scientists define a suite of biosignatures that go beyond specific molecules. There is chirality, the left or right-handedness of molecules. Life on Earth prefers one-handedness for amino acids and another for sugars. Non-biological chemistry tends to make equal mixes, so a strong bias in chirality is a clue. There are isotopic fingerprints, where life tends to prefer lighter isotopes of carbon or sulfur, leaving a subtle shift in ratios that can be read in rocks. There are networks of molecules and certain distributions that betray metabolism. There is the organization of cell-like compartments, membranes, cell walls, and the patterns they make when they crack or fossilize. There are complex lipids, too elaborate to form easily without cellular factories. Instruments like mass spectrometers and Raman spectrometers on rovers can scan for these patterns. A careful ensemble of tests, in which multiple independent clues point in the same direction, builds a stronger, quieter case. We also learn from absence and silence. False positives are as important as true ones. Can oxygen arise without life? Yes, through photochemistry and loss of hydrogen. Can methane be forged in rocks? Yes, through serpentinization in water-rich, iron-rich environments. Can organics arise without biology? Absolutely. Interstellar space is a chemical kitchen. Meteorites bring down rings and chains of carbon unmade by hands. The craft is to see combinations and contexts that make biology more likely, not to be seduced by a single pretty hint. To keep us steady, NASA and its partners invest in analog sites on Earth. There are teams in the Atacama Desert hiking uphill into regions so dry that some soils have almost no microbes at all. There are researchers under Arctic ice, drilling through blue silence into brine channels and reaching for life under pressure in darkness. There are divers in acidic hot springs in Wyoming and neutral vents on the ocean floor where white chimneys grow and fluids mix. Each place teaches us what life's edges look like and what signatures stay intact when wind, sun, and salt try to erase them. And in the stream of data, there is a consistent practice. Open archiving, methodical reporting, calibrated humility. NASA's planetary data system stores raw and processed measurements so others can test claims. Teams pre-register how they will analyze data. They compare results across instruments. They publish not just their plots, but their code and their assumptions. Those confidence ladders and reporting standards are not for show. They are there to help our tired hearts when excitement threatens to run ahead of evidence. It is a kindness to the future to be this careful. On the exoplanet side, the imagination keeps expanding. Think of a distant map drawn from light curves, continents painted by brightness swings, clouds blurring edges, polar caps glimmering. Think of a green edge not at our red, but shifted for a different star. A plant-like pigment tuned to harvest a red dwarf's glow or a brighter blue sun's light. Think of a purple Earth, where certain microbes dominate, painting the world with a different spectral brush. Think of a planet with seasonality carbon dioxide, exhaled in winter, inhaled in summer, seen as a gentle breathing over months, across light years. Each of these is a biosignature, not in a single molecule, but in a pattern over time. Now breathe. Notice the steady pace of it all. From a rover's tire track to an infrared rainbow from a star we will never visit, the search is a meditation, not a race. In the last chapter of this story, we face forward. We ask about what comes next, and what it means for us to be the kind of species that can listen so carefully that a planet's breath can be heard in starlight. The future of NASA's search for biosignatures is made of patient plans and careful dreams. Some are already on their way. Some are still drawings and quiet meetings. All of them feel like extensions of a single gesture, a hand cupped to the ear, listening in the dark. In the coming years, the Roman Space Telescope will test coronagraphy at a level of finesse we have never flown. It will teach us how to sculpt starlight inside the telescope itself, carving a dark hole in the glare where a planet can hide. This is not by itself the machine that will reveal an Earth twin, but it is rehearsal with real stars. It is the fine motor practice that makes a musician's hand sure. Concepts like starshades remain on the table, delicate flowers of engineered darkness. They could one day float in formation with a telescope, suppressing a star's light by orders of magnitude and letting the faintest of planets emerge. Farther ahead, the Habitable Worlds Observatory takes shape in studies and community conversations. Its stride is long. It would be built to find and characterize Earth-sized planets around sun-like stars, to read their skies in visible and near-infrared light, to look for water vapor, oxygen, ozone, methane, and surface hints like glint and edges. Wrapped into the plan is the experience of everything learned so far: how to keep optics steady, how to measure and subtract the telescope's own ghost light, how to calibrate a spectrum so that a small notch in a rainbow isn't just a wrinkle in a mirror. Any such mission would be a cathedral of patience, requiring quiet engineering virtuosity and decades of care. The key, though, is not the machine alone. It is the community and the method, the ladders of confidence, the open data, the willingness to sit with ambiguity until more light arrives. Complementing these dreams are ideas for mid-infrared observatories that can hear the heat of Earth-like worlds more directly. In this band, some biosignature gases speak more clearly. Ozone's strong line in the mid-IR, carbon dioxide's deep groove. Methane's distinct voice might be read with less interference from clouds. Interferometers, which combine light from multiple telescopes to create a bigger virtual mirror, have been imagined as ways to reach that sensitivity. Such missions are hard, luminous challenges. They are also part of the conversation, because time has taught us that life may whisper in one color where it is drowned out in another. Back at Mars, the story continues in parallel. Perseverance's cached samples wait for the choreography of retrieval and return. Clean rooms will receive them. Scientists will be ready with instruments that can see molecules one by one, count isotopes with exquisite precision, and map layers in rock thinner than a hair. On Europa, Clipper will fly and taste. On Titan, Dragonfly will beat its wings in thick air and listen to sand. Enceladus waits for a mission aimed squarely at life detection. And in the meantime, laboratories on Earth recreate its ocean chemistry in steel and glass, measuring what life would make and how to see it in a plume. There is one more thread we have not pulled fully. Technosignatures, the clues of technology, the side effects of a civilization's presence. NASA's biosignature search is focused on life as nature grows it. But in the same rooms and teams, some scientists consider narrowband radio, odd atmospheric industrial chemicals, nighttime lights, too regular to be natural. They keep this thread gentle, careful, speculative, but precise. If it ever appears in the tapestry, it will be woven with the same measured voice. An observation, a context, a cross-check, a scale of confidence. What does all of this mean for us as we lie back and listen? There is a softness to the answer that feels like night. We are learning that the universe is not stingy with planets. We are learning that oceans can exist under ice in the cold, that chemistry explores every stage from simple to complex wherever it can. We are learning the humility to be slow. The first real biosignature we confirm, if it comes, may not be a trumpet. It may be a steady, clear tone, a balance of gases out of equilibrium, a seasonal swing, a pigment edge repeated across observations until doubt runs out of places to live. It might also be that we look for a long time and learn instead how rare our own arrangement is. A planet that stayed calm enough for long enough for life to learn to breathe oxygen and paint a surface green. A star that did not rage too much. A magnetic field that held. A moon that steadied the tilt. A history that let seas whisper for billions of years. That, too, would be a gift, because it would turn our attention home with gratitude and care. In the quiet rooms where these searches begin, there are rituals of kindness. Engineers run their hands along the edge of a mirror, carefully gloved, and think of how light will flow. Scientists label a vial with tiny handwriting and check it twice. Teams pause before sending commands to a spacecraft, breathing together. There is poetry in this patience. There is also a sense of companionship. We listen to other worlds, not to be less alone, but to learn the full shape of life's possibility, to feel the larger pattern we are a part of. One night, perhaps, the data will settle into a shape that feels like a hand extended. Maybe it will be a planet with a small ocean's glint, a balanced sky that refuses to settle, a soft edge in the red that suggests leaves of a kind we have never seen. We will check and check again. We will share the data. We will ask others to measure it anew. And then, gently, we will say, we have heard a living world. Until then, you can rest in the knowledge that the listening is real, careful, and ongoing. Between now and whatever comes, there are stars to watch, light to sift, and a planet under your feet that is, itself, the most generous teacher in the cosmos. If you'd like to drift with us in more of these quiet night journeys, stories that breathe slowly, science that feels like a lullaby, you are warmly welcome to stay, to subscribe, and to return whenever you need a gentle window to the sky. Sleep well, and let the starlight speak.